Got another question for the synoptic questions playlist, so we're up to number 16 now. As always, the link to the questions in the description of the video if you want to try it first. Okay, so the first thing I'm going to do is calculate the energy produced by the reaction that's taking place in that polystyrene cup. So we're using the Q equals mc delta T equation. So M is 50.7. Remember it says about 50 cm cubed of H2O, so we're not meant to use 50, we're meant to calculate the actual mass of solution. So that was the difference between those two numbers there from the table. Multiplied by C, which we're told is the same as water, so 4.18. Multiplied by the delta T, the temperature rise, which is the difference between those two numbers. So that gives us 2861 joules, which is 2.861 kilojoules. Next thing we do is work out how many moles of copper sulfate were involved in the reaction. So mass over MR. The mass is the difference between those two numbers, and that comes out at 0.05 moles. So the enthalpy change of solution is the enthalpy change per mole. So we divide the kilojoules by the moles, which gives minus, it's exothermic remember, the temperature of the solution went up, so minus 57.22 kilojoules per mole. So we'll now move on to the cycle and the calculation of the enthalpy change for reaction 5.1. So we've got to calculate the enthalpy change for this reaction here. We've just calculated the enthalpy change of solution for copper sulfate. So you can see that ties in with this arrow here on the cycle. And we were supplied with the enthalpy change for this reaction. This is 5.3. Obviously, if you dissolve that into water, you're going to make these aqueous ions just like this one. So we've got this cycle here. So applying Hess's law, we can go straight across the top, or we can go around the bottom. So you'll notice that the bottom route, this arrow here, is going in the wrong direction. So the enthalpy change for 5.1 is equal to this one here minus this one here. So subbing the numbers in obviously gives us that, which gives an enthalpy change for 5.1 of minus 65.65 kilojoules per mole. Moving on to the final part of A, where we've got to calculate the temperature change in experiment 2. So we're told that the uncertainty in each temperature reading is plus or minus 0.1 degrees C, and the students calculated a 20% uncertainty in the temperature change. So there's the formula we use. Percentage uncertainty equals the uncertainty value, so that plus minus value, divided by what's measured, multiplied by 100. So we want to calculate what's being measured, so it rearranges to this. Measured equals uncertainty over percentage uncertainty times 100. So substituting the numbers in gives us this, but because we're calculating a temperature change, we double the error, because there's an error in the initial and final temperature. So that's why that's being highlighted and that there. So putting the numbers in gives a temperature change of 1 degrees C for experiment 2. Moving on to part B now, we've got to calculate the entropy for sodium thiosulfate. We already know the entropy of the H2O and the hydrated sodium thiosulfate. It's there in the table there. We've also got the delta G and the delta H for this reaction. So the way we're going to get to the answer, we're going to use the Gibbs equation to calculate delta S. Obviously we're going to have to rearrange it first. So we'll calculate delta S, and then we're going to use this equation here to calculate the entropy of the sodium thiosulfate, which is going to be one of the reactants in the equation. So subbing the numbers into the Gibbs equation, we get this here. Rearranging gives us this here, which comes out at minus 39.7. So to get delta S, we divide that minus 39.7 by 298, which gives an answer of minus 0.133 kilojoules per Kelvin per mole. The delta H and the delta G that we've used have got kilojoules per mole units, so that's why the kilojoules are there. You'll notice in the entropy values though we've got joules per Kelvin per mole, so we need to turn this value into joules per Kelvin per mole. So obviously we do that by multiplying by 1000, so the delta S is minus 133 joules per Kelvin per mole. So now we've got that delta S value, we can bring in the equation that helps us calculate delta S. Remember, we want to calculate the entropy of one of the reactants, the sodium thiosulfate. So I'm just going to put the numbers into this now. So we get that there. The X obviously represents the entropy for the sodium thiosulfate, and this is the 5 times the H2O value. So all we need to do now is isolate X and find out its value. So losing the bracket just gives us that expression there. So all we need to do now is take the minus X over to the left hand side, becomes plus X. We take that minus 133 over to this side and it becomes plus 133. So the answer is coming out to 3 significant figures of 156. The calculated value was 155.9, which obviously needs to go to that. Moving on to part C now, we've got to calculate this OSS bond angle. Well, we're talking about the angle around this central sulfur here. So I'll just highlight that. So we've got to think about what kind of electron regions we've got around this central sulfur. So around the sulfur we've got 4 bonding regions. So we've got 2 single bonds and 2 double bonds, but they all just count as a bonding region each. There's no lone pairs around the sulfur. All of the valence electrons are going into these bonds, so therefore we're going to have equal repulsion. So the angle around that sulfur is 109.5 degrees and the shape is tetrahedral. So moving on to the last part, we're told that the S4062- ion is a dimer of the thiosulfate ion, so obviously we need 2 of these, so we just need to think about how they could join together to form the S4062- ion. So there's one of the possible answers. So we've joined the 2 thiosulfate ions together via the O minuses. Alternatively, you could have that, where the 2 S minuses have joined together and created the bridge there. You could also have this, where the S minus, say, of this one bridges with the O minus of the other one. Or you could do it the other way around.